Okay, in this video, we'll be talking about the electric potential and electric potential energy. Electric potential is V. Electric potential energy is U. Electric potential at a point is the work done in bringing a unit charge from infinity to that point. Electric potential energy of a charge Q at a point is the work done in bringing the charge Q from infinity to that point. If you are asked to give the definition of the electric potential or the electric potential energy, then this should be your answer. Remember, for the potential, it is only one unit charge, but then for the potential energy, it is an unknown amount of charge Q. Okay, so now we want to move a point charge capital Q from point A to point B in an electric field, and then that electric field is caused by a charge small q at the origin. Okay, so you want to move Q from here to here. The distance you move is dl. Okay, the distance between point A and origin is RA. The distance between point B and origin is RB. And then the work done by an external agent in displacing the charge Q by a distance dl is dw equal to negative F dot dl. Remember, when I want to find the work done by the external agent, there will be a negative sign here. If now it is the work done by the electric field, therefore the negative sign disappear. Okay, so now F equal to QE. And then you integrate it to find the work done. And then we define VAB equal to electric potential at B with reference to A. Remember that I use the word define because actually the electric potential depends heavily on your definition. Different textbooks might have different definition of the electric potential. Therefore, you really have to check for the definition very well. Okay, so now we define VAB as this. So VAB equal to W over Q equal to this one, and then you do your mathematics. Okay, so at the end of the day, you will realize that VAB equal to VB minus VA, which is equal to electric potential at B with reference to A. But once again, this really depends on your definition. Some textbooks can have VAB equal to VA minus VB. It is also equally correct. It just depends on your definition. Okay, so by using our definition here, if VAB is positive, that means that VB is greater than VA. So point B is at a higher potential than point A. And then there's a gain in the potential energy in the movement from point A to point B. So an external agent performs the work. Okay? Who is the external agent? The external agent is just simply you. Okay? Let's say you use your hand to point this, to put the point charge Q from here to here, then your hand is the external agent. Okay? So now once again we use the definition that when R equal to infinity, the electric potential is 0. Okay? But generally this definition is surely correct for all human beings. Normally we as the human like to define the potential at infinity is 0. Okay? So VAB equal to this one. And then you know that RA is infinity, so everything divides by infinity is 0. It will approach 0, okay? Then we say that the electric potential at any distance r from a point charge Q at the origin is V equal to this one. Okay? Remember, electric potential at any point from the point charge small q at the origin is this. Okay? So you know that the electric potential is not contributed by the capital Q. Okay? Because the capital Q has already been divided. Okay? So now, once again, the electric potential at any point is just the potential difference between that point and a chosen point at which the electric potential is 0. Normally, we define the chosen point is a point to be infinitely away from us, okay? Which is very far away from us, maybe from the edge of the universe, maybe, okay? And then I need to tell you that what do we mean by higher potential is that the potential has a more positive value. What do we mean by a lower potential is that the potential has a more negative value. Okay? When you look at this, maybe you think there's no problem. But then when it comes to gravitational potential, it's a disaster. Because for the gravitational potential, there's a negative sign here. Okay, so let's say now this is the mountain, and then you are here. This is the top of the mountain. This is a region very, very high in the sky, okay? Very far away from the earth. Because there's a negative sign in the gravitational potential. Therefore, you know that when you are here, you experience, let's say, negative 100 volt. And then let's say you are now on the top of the mountain. Then at this moment, you can feel negative 10 volt. Okay, let's say now you are on a rocket and then you go to the universe. Then you are very, very far away from the earth. Then now you can feel 0 volt. Okay, then we say that 0 volt is the highest potential, is the highest gravitational potential. And then the negative 100 volt is the lowest gravitational potential. Why I have to stress this is that if we do not tell the students like this, normally the students will think that this is the higher potential because they say that there's a value of 100 here. And then the students will say that this is a lower potential because you see the magnetic is 0. But then this is totally wrong, okay? This is more positive, so this is a higher potential. This is more negative, so this is a lower potential. Please remember this. Okay, now let's say you are here and then you want to climb out the mountain. So you want to move from a region of low gravitational potential to a region of high gravitational potential. You have to use your energy to climb out the mountain, right? So you are performing the work so that there is a gain in the gravitational potential energy in the movement. Let's say now you are already on the top of the mountain and then you want to come down. You don't even have to use energy, you know. You just straight away jump off the cliff. You just straight away jump off the mountain, then the gravity can help you to do the work. Okay? So that means that you do not do the work, but the gravity performs the work for you. So there is a loss in the gravitational potential energy in the movement. Okay? Okay, so this is what we have learned in the gravitational field. Let's come back to the electric field. Let's say in an electric field, you have a positive point charge. You know that the positive point charge will tend to move to the region of lower electric potential. So, if the positive charge makes this movement, then the work is done by the electric field, and then there's a loss in the electric potential energy. But then if you want the positive charge to move to this direction, then you have to use your own energy to perform the work so that the positive charge can move this way. And then we say that there's a gain in the electric potential energy. Okay? Then what if you have a negative point charge? The negative point charge will tend to move to region of higher electric potential. That means that if the negative charge is moving this way, then the work is done by the electric field, and then there's a loss in the electrical potential energy. But then if you want a negative charge to move this way, then you have to do your work done. Okay? So that you use your own energy to move the negative charge this way. Alright, so that there's a gain in the electric potential energy. Okay, so now please draw an electric potential graph for the following. This is positive charge, this is also positive charge. So you know that the potential at here is extremely high. Okay, we have a very high potential here. And then when the distance from the point charges increases, the potential will decrease. And then it will approach zero when the distance is at an infinity, is very far away from us. Okay, can you find a position where the electric potential is zero? No, the potential, even if I want to find the position, then the position should be x equal to plus or minus infinity away. Okay, that means that they are very far away, so that they can never feel the potential now. Okay, but I would say there's no position where the electric potential is zero. Okay, and then let's take a look at this. One is positively charged, another is negatively charged. So this region is highest potential, this region is lowest potential. Okay, can you find a position where the electric potential is zero? You use the formula for the electric potential. The formula for the electric potential is Q over 4 pi epsilon 0 R. Okay, then you have to remember that for the electric potential, because electric potential is a scalar quantity, that means that they do not have the direction. That means that you straight away add them up. Okay, you use the superposition theorem for the electric potential. Okay, so you know that when x equal to 0.333 meter, the electric potential is zero. But then for here, even if you want to find a position where the electric potential is zero, we can only say that maybe it's at x equal to plus or minus infinity. Same case for here. Okay, because we normally define a point which is infinitely away from us will have the potential equal to zero. This is the common human definition. And then you have to remember that okay, I will introduce you to the formula later on, but please remember that the steeper the graph of the potential distance graph, the greater the magnitude of the electric field strength. That means that if here is very steep, right, then the electric field here is very strong. This is horizontal, right? This almost has a horizontal gradient. That means that the gradient is almost equal to zero. Therefore, you will say that the electric field strength here is zero. Okay, this is very steep, right? So you know that the electric field strength here is very strong. Okay, the steeper the graph, the greater the magnitude of electric field strength. But when the gradient is zero, that means that there is no electric field strength. Okay, there are now 3 point charges. Please find the electric potential at point P. You just use the superposition theorem to add them up. And then please find the work done to bring a charge of negative 17 nanocoulomb from infinity to point P. Then you will say that the work done equal to Q delta V, where the delta V is the difference between the potential, okay, which is equal to the final potential minus the initial potential. Okay, the final point is point P. The initial point is from infinity away. When you know that it's infinity away, then the initial potential must be zero, because this is our human definition. Okay, now point charges Q1, Q2, and Q3 are located at the verticals of an equilateral triangle Q1, Q2, Q3. Please find the electric potential at the center point X of the triangle. Okay, first you have to know the distance between the point X and the individual point charges. That means that you want to find the distance from here to here. You want to find the distance from here to here. You want to find the distance from here to here. The distance is this one. Okay, you use a powerful trigonometry. You use a powerful geometry to solve for distance between point X and the individual point charges. Then only you can do the superposition theorem of your potential to find the final potential. Okay, because electric potential is a scalar quantity, so you do not have any direction. Okay, So remember that the electric field line will point from the region of higher electric potential to region of lower electric potential. For example, you remember that the electric field strength from a positive point charge will point away from the positive point charge. That means that here has a higher potential and here has a lower potential. And then for a negatively charged particle, the electric field will point towards the negatively charged particle. So you know that here has a lower potential, here has a higher electric potential. And then this is a parallel plate capacitor, okay? Then this is positively charged, this is negatively charged, and then the electric field will point from here to here because the electric field will point from the region of higher electric potential to region of lower electric potential. And then now I want to introduce you something which is equipotential surface. The equipotential surface is a surface where the electric potential at every point on that surface are the same. That means that the electric potential at this point is 100. This point is also 100. Also 100, also 100, also 100, also 100, also 100. So you say that this surface, okay, this is a spherical surface, is an equipotential surface. Okay, for example, this one, which is just a plane surface. All right, you know that the potential here is equal to 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 the potential here. So this plane is an equipotential surface. Okay, and then you notice that the equipotential surface must be perpendicular to the electric field. The equipotential surface must be perpendicular to the electric field. The equipotential surface must be perpendicular to the electric field. The equipotential surface must be perpendicular to the electric field line. Okay. So now let's say you are considering a dipole. Okay. When there are 2 point charges of equal magnitude but of opposite sign, you call them dipole. And then for this dipole, I remember that there is one question asking you to find the equipotential surface where the potential is 0. Then the answer is just this one. Okay, on this surface, that means that on this plane surface, V is equal to 0. Okay, and then now you know that positive charge has a higher potential, negative charge has a lower potential. And then you notice that when the equipotential surface is very close to the point charge, it is almost like a perfect spherical surface. But then when the distance of the equipotential surface from the point charge is increased, that surface becomes less spherical. Okay, that means that the surface becomes more elliptical. Okay, so that means that this distance is much shorter than this distance. Okay, this distance is much shorter than this distance. Okay, and then you know that when the equipotential surface gets closer to the negative charge, it is more negative. That means that this region has the lowest electric potential, and then this region has the highest electric potential, and then this region, the green line here, has the 0 volt, which is in between. Okay, then you also notice that the equipotential surface and the electric field line is perpendicular. That means that they always form a 90 degree. Okay, 90 degree. Okay, they are perpendicular. All right, they are perpendicular for every equipotential surface. Okay, perpendicular. This is very important. And then why it is perpendicular? Let's say now if the electric field line is not perpendicular to the equipotential surface, then surely you can find the component of the electric field along the equipotential surface. But What do we mean by the electric field is that E equal to negative dV dr. If there is a non-zero electric field, that means that there will be a change in the potential. But just now we say that the equipotential surface must have a constant electric potential on every point on that surface. So surely we cannot have any component of electric field along the equipotential surface, and that's why E must be perpendicular to the equipotential surface, so that E cos theta, and then the theta is 90 degrees, which is 0. So we have to make sure that there is no electric field strength along the equipotential surface, so that the equipotential surface can really have a constant potential. Let's do a question. Electric field due to a point charge Q is shown. The electric field points towards the point charge Q. That means the point charge must be negatively charged. And then the lines are equipotential lines. Sorry, this one is electric field line. If you want to draw the equipotential lines, then the equipotential line should be this, the blue one. Okay, the equipotential line, the equipotential line. Normally we don't call it equipotential lines, we call it equipotential surface. Okay, because it's really a surface instead of a line. If you want to say it's an equipotential line, then it's the wire you are using in your direct current series. Okay, I think I'll show you the equipotential line first. Inside a direct current circuit, we assume the wire is a perfect conductor, and therefore when the wire is a perfect conductor, there should not be any resistance in the connecting wires. Therefore, the wire is an equipotential line. For example, if I cut this circuit and then I plot a potential distance graph of this, then you will notice that this is an equipotential line, this is an equipotential line, this is an equipotential line, and this is also an equipotential line. Okay, but then in this question, because it's a surface, so we call it they are equipotential surface. Okay, for example, this blue one shows the equipotential surface. The magnitude of electric field increases with the increase in distance from the point charge. No, the magnitude of electric field will increase with the decrease in the distance from the point charge, because E is inversely proportional to R squared. The direction of the lines shows the direction of force experienced by a test positive charge. Yes, because a positive charge will move from region of high potential to low electric potential, and then the direction of the E is from high potential to low potential, so the positive charge will move to here. So yeah, this is correct. The direction of the E is same as the direction of the force experienced by a positive charge. Okay? Okay, so now we want to prove that F equal to negative du over dr and E equal to negative dv over dr. I think I will leave this one for yourself to read. Okay? But remember, we really have to remember F equal to negative du over dr. U is the electric potential energy. V is the electric potential. Okay? So for example, let's say now you are given a graph like this. You know that U changes like this. You want to sketch a graph to show how the F will change with the distance. You know that F equal to negative du dr, so you have to use this formula. From here to here, U decreases constantly. Du is a negative number. A negative number times a negative sign becomes a positive number. From here to here, U increases constantly. Du is positive, so it times a negative sign, it becomes a negative value. From C to D, wow, it increases sharply. So du is a very great positive number. But times when it comes to a negative sign, it becomes a very negative number. From D to E, the u does not change. That means that u is a constant. Du is 0, so everything becomes 0. Okay, so this is how you get the answer. Okay, by the same reasoning, except that now u changes to v and then f changes to e, you repeat all the steps here, then surely you can get this answer. Okay, I will leave this to your own homework to do, but it's just the same reasoning. You find out the gradient, then you times a negative sign, then you can get the answer. That's all. Okay, so now electric field strength of a uniform electric field. This is a parallel plate capacitor. You know that the electric field will point from here to here. And then this is an equipotential surface. This is another equipotential surface, and so on. And then the electric field will point from here to here. Okay? And then the equipotential surface will form a right angle with the electric field lines. Okay, so now you have to remember that E equal to negative dV over dr. When it comes to uniform electric field, that means that the electric field has a constant magnitude everywhere in between the parallel plates. Then only you can use E equal to negative delta V over D. Delta V is the difference in the electric potential between two plates. Okay? And then when we want to consider the magnitude of the electric field, we ignore the negative sign. Okay, so the electric potential with the distance graph is shown like this. This is at a higher potential, this is at a lower potential, and then the electric field is a uniform electric field. So you know that the gradient is a uniform gradient. That means that the gradient is just a constant. Okay, so now please, given that V1 equal to positive 100 volt, V2 equal to negative 100 volt, the distance between the plates is 2 cm. Please find the electric field strength. Electric field strength equal to delta V over D. Please find the electric potential Vx, which has a distance 1.2 cm from the metal plate of V1. Okay, so find the electric potential along this line, along this surface. Okay, so you use the formula this. Electric field equal to the difference between the potential divided by the distance. Okay, once again, you can only use this when the electric field strength is constant in between the parallel plates. Alright, okay. Actually, I need to tell you that for a parallel plate capacitor, actually we have the fringing effect. The fringing effect is like this. Okay, that means that the electric field has a curve on the edges of the capacitor, but normally we make sure the capacitor has a dimension such that the area is much larger than the distance between the parallel plates, so that the fringing effects will have a very small effect. That means that we can ignore the fringing effect. So normally in STPN, you will never hear of the fringing effect. Okay. So this graph shows the electric potential V with distance r from the center of a charged conducting sphere of radius r. Okay, please find the graph of electric field strength E with r. E equal to negative dV dr. Okay, so let's take a look at the constant potential first. When the potential is constant, dV is 0, so you know that there is no electric field at all. So when r is smaller than capital R, V is constant, E is 0. Okay, let's take a look at the red region here. The V is decreasing sharply. dV is a very negative number, but when it multiplies with negative sign, it becomes a very positive number. Okay, and then for the purple region here, V decreases slowly. So you know that dV is a very small negative number, and when it multiplies with a negative sign, it becomes a small positive number, which shows the resultant electric field when a conducting plate is placed in between two parallel metal plates. One is positively charged, another is negatively charged. You have to remember that the conducting plate is an equipotential body. And then you also remember that the electric field must be perpendicular to the equipotential body. That means that the electric field must be perpendicular to the conductor. Perpendicular, okay? 90 degree, 90 degree, everything is 90 degree. And then you have to remember that inside a conductor, the conductor is an equipotential body, so there is no electric field inside the conductor. So this one is wrong. This one is also wrong because there should not be any electric field inside the conductor. Okay? You have to remember that if there is really electric field inside the conductor, then what will happen? The free electrons in the conductor will be accelerated, so there will be some current in the conductor. But what chapter is this? This chapter is about electrostatic. So of course, there will not be any current inside the conductor, so there should not be any electric field strength inside the conductor. Okay, so these two are definitely wrong. Okay, and then you have to remember that electric field line is always perpendicular to the equipotential body. Okay, so in the next video, we will talk about electric potential energy, which is a continued version of this, and also the work done in positioning some point charges. Thank you.